Hello, I'm Hyun-Sung Choi from Team16. From now on, I'll present a project proposal. Our project topic is network pruning. Network pruning is a technique that makes a dense network sparse while maintaining accuracy so that reduces space and time complexity. It is usually considered in limited resources environments. However, many of the previous pruning methods have the following problems. First, pre-training is essential. Generally, pruning algorithm is pre-training, pruning, and fine-tuning pipeline. Among them, pre-training means training dense network before pruning. A pre-trained dense network gives information helping to determine the way to prune. However, this process requires many resources generally. Second, fine-tuning is also essential. Fine-tuning is the technique tunes the unpruned weights inherited from trained dense network to obtain original accuracy. Fine-tuned pruned network shows better performance than the pruned network trained with randomly initialized weight. However, the need for fine-tuning means that pruned network cannot be trained independently from dense networks. In this project, we will try to simplify the pruning pipeline by eliminating pre-training and fine-tuning. Once these two problems are resolved, we can expect to obtain pruned network independent of dense network more efficient way.
Hello, I'm Youngji-go. In this section, I'd like to explain the related work. A number of recent studies have shown that the problem mentioned before can be solved by eliminating pre-training and fine-tuning. I will introduce three papers among them. The first is Rethinking the Value of Network Pruning, which is accepted by ICLR 2019. The author of this paper identified that fine-tuning is not necessary. In the picture, you will see the network pruning pipeline proposed by the author. They proposed to train prune network from scratch instead of fine-tuning. This method achieves better performance than fine-tuned network. Second, there is pruning from scratch that is accepted by AAA 2020. The author improved the network pruning pipeline proposed by the paper mentioned before. They also proposed a new pipeline to remove pre-training and fine-tuning from existing pruning algorithms. This method achieves same or even better performance than the baseline network. The last one is single-shot network pruning based on connection sensitivity, which is accepted by ICLR 2019. The author introduced new pruning method based on connection sensitivity. Connection sensitivity implies importance of each way connection. The new approach prunes a dense network once at initialization prior to training, so it does not have to pre-train or fine-tune. In the bottom of the slide, the figure shows that the proposed method eliminates the heuristic elements and pre-training, and it achieves comparable and even better performance than existing pruning method.
Hi, my name is Sunyoung Kim, and I will announce the replication approach. Among the related work introduced above, we selected SNP, single-shot network pruning based on connection sensitivity, as the replication paper. The reason we chose SNP paper is as follows. First, SNP has high feasibility. SNP is very simple to implement but powerful. In contrast, in the case of rethinking the value of network pruning, this paper conducted and compared experiments using various network pruning algorithms. There would be difficulties in understanding and implementing all algorithms. Considering the fact that replication and improvement experiments should be conducted within a limited time, we thought that SNP was more realistic. Second, SNP is easy to improve. SNP has much plenty of room to improve. For example, SNP only experimented with small data such as MNIST, so we can experiment with large data that is commonly used such as ImageNet. Besides that, there are many other things to improve in SNP.
Hello, my name is Chunmyong Park, and I will tell you the rest of the proposal, including the improvement approach. Our first improvement approach is to apply an ImageNet. This paper only experimented with small data such as MNIST, Cyber10, and Tiny ImageNet. But in order for research to be practical, SNP need to be experimented with large data such as ImageNet. So we will try to improve SNP to work well with ImageNet. The second is to apply warm-up. SNP prunes the network based on the connection sensitivity calculated from the gradient. However, according to Facebook's paper, the gradient which is obtained right after initialization is unstable because it changes rapidly in initial training. So we'll try to obtain stable gradient using warm-up proposed by Facebook before SNP. We expect that SNP will get better performance using this stable gradient. Next, the list of data we'll use for the experiment. In the application, we would like to experiment with the MNIST, Cyber10, and Tiny ImageNet used in the paper. In improvement, we'll use ImageNet. Lastly, I will explain our project schedule with the Gantt chart. The Gantt chart contains information about the activities, the person in charge, and the time required. First of all, we're going to focus on application in May. And we want to finish all activities before submitting the progress presentation. In June, we are going to focus on the improvement. The schedule is similar to that of May, and will also be completed before submitting the final report. This slide shows the reference list, and you can check out the paper we referred to. Let's finish our project proposal presentation. Thank you for the listening.